now. So what I thought we could do, I'm not sure if you guys think it's the best strategy, but I thought that we could really just read. It's 10 pages long, this text. I thought we could just like, I don't know, share the reading, you know, like each one read one page and we rotate and discuss it whenever you guys feel like we should stop. But just so we actually go through it together, I think that being so short in this way, we don't need to, you know, risk that any kind of attempt to summarize it is leaving something important out, you know, too soon.
Okay, so this is chapter 9.
Yeah. I can leave it on the screen and just go down as well if you prefer to read it straight from.
Yeah, in the intro also to this part, he goes through, it's a few extra pages, but he goes through like genericity, but it's also like kind of a summary of life itself.
Yeah, it's weird because he says this in the beginning that I devoted chapter 2 of life itself to this concept, but in the book, the discussion is actually genericity, actually just in terms of the general and the special, you know. And it's interesting because the generic and the general don't seem to be exactly the same, though that's clearly one of the main kind of contents of the word for him, right? I'm not sure what you guys think, if we should, I mean, if we should also read this preliminary statements. I think that they might be a bit too general, you know, and perhaps we can just, since they're meant to just summarize the next pages, we could just start from the chapter itself.
Okay, let's skip this intro.
Does anyone want to start, or I can do it as well?
Yeah, I can start.
Okay.
Great. All right, the appearance of Ring Tom's Stabilité structurelle et morphogénèse in 1972, translated into English in 1976, was a watershed event in mathematics, in theoretical biology, and for the philosophy of science generally. The questions he raised in that book, both directly and by implication, were deeply disquieting to most practicing empirical scientists, making their dogmatic slumbers untenable. Their predictable responses took several forms. 1, outrage and indignation. 2, violent but irrelevant counterattacks. 3, pretense that Tom did not exist, and hence that his ideas did not need to be addressed at all. And 4, a distortion of his views into a benign soporific that would enable them to sleep again. Indeed, most of the truly radical aspects of Tom's book have never been discussed at length. The book itself is largely viewed as a wrapper for the classification theorem. But that theorem, conspicuous as it is only the tip of an enormous iceberg. I will go beneath the water a bit to explore some of the architecture of that iceberg, especially that concerned with the implications of genericity for science in general, for the deeper relations between biology, physics, and mathematics it reveals, and above all, for the theoretic and philosophical principles buried in it. A prominent part of this discussion will comprise a few of the linguistic aspects to which Tom was increasingly drawn over the past few decades. I would like to dedicate this chapter to Ring Tom, a man whose intellect, vision, and above all, character are all too rare in today's drab world. I hope it will serve to capture some of his spirit.
Just to clarify, like before we go on, like, I mean, I'm not sure if you guys ever took a glimpse, open Tom's book, like this structural morphogenesis, structural stability and morphogenesis. But it's I mean, by looking at it, I would never assume that it's a wrapper for the classification theorem. Like,
yeah. Now I'm interested in what is the classification theorem.
So yeah, I read the intro. He talks about it's the classification theorem of singularities specifically. I don't personally actually know that much about this in particular. A little bit, I mean, but not about this specific theorem. But it says that one thing that's interesting is it shows that it says on the Wikipedia, it says that stratified sets were developed which is related to his work on the classification theorem of singularities, was developed as to understand the notion of topologically stable maps and to eventually prove the result that the set of topologically stable mappings between two smooth manifolds is a dense set. And that's the important part, which a dense set is very similar to the concept of genericity, because a dense set is basically one that intersects any neighborhood. So any tiny neighborhood of that topology will be intersected by it. So like the rational numbers or something. So that might be where the connection is to a degree, but I don't know enough to really speak about it a lot.
Yeah, I know that, I mean, from the kind of philosophical reception of the book, I know it was taken as a sort of first step in a mathematical theory of the quality of forms. Like it was supposedly like the next big thing after that Darcy Thompson, I forget, the guy who wrote Growth and Form, a theoretical biologist studying, let's say, what counts as a form in living creatures, and also making connections between sort of formal analysis and other, let's say, stable forms in nature, like whirlpools and things like this, right? And trying to give credence that there is something like a qualitative treatment of these things that is more enmeshed with the quantitative approach, with classic mathematical approach. And usually people put it in the same kind of camp as Mandelbrot's work on fractals and things like this, things that look like they're bringing us closer to nature's complexity, and they're dealing with complexity in a way that are approaching something that is recognizable in nature, things like this, right? But it's also the kind of big book for what afterwards was known as like chaos theory and catastrophe stuff, right? But more than that, I really don't know. But he doesn't really, I mean, it's weird. His take, I always find Rosen weird because he doesn't use the third, like he's never reading people the way that they're usually read, and he says like it's obviously this and that, but nobody really agrees with him. So I'm not sure how to read
that.
this.
I can read this next section if you want.
Okay, sure.
So it's on theory and biology. To someone familiar with mathematics, the word theory has no pejorative connotation. Quite the contrary. There's no opprobrium attached to those who study group theory or number theory or the theory of functions of a complex variable. And there is no inherent opposition between those who study such theory and those who study particular instances to which it applies. In science, however, this situation is quite different. Here, the word theory carries an inherent pejorative connotation. Why? Because science lusts for objectivity, which associates entirely with one, the study of particulars, and two, what linguistics call context independence. When science is emancipated from the anthropomorphic elements, see Bergman on Max Planck at the beginning of chapter 5, only particularities are left, and not even all of them. Theory is essentially associated with intrusions of the structuring mind, Bergman again, mental constructs superimposed on real, objective, particular facts, contaminants of science, of science, and of particular objective data that are alone to be allowed. Hence, theory connotes the purely speculative, and a false opposition between objective empirics and subjective theory is created, in which the former is good and the latter is bad. Nowhere are such misconstructions more prominent than in biology, especially in the minds of empirical biologists. Modern biologists are simply ashamed of their own intellectual history. Almost as an ethnicity, they wish desperately to repudiate. They want to be assimilated as scientists among scientists, but they bear a historical cross in the form of millennia of speculations involving finality, vitalisms, and homunculi of all kinds. They also dread alienation from their own field by the advance of, to them, incomprehensible mathematical developments. This simmers even in physics, usually below the surface, but occasionally erupting into open view. A unique, unprecedented, and quite spectacular example was provided earlier in the century in the form of what was called Deutsche Physik, or Aryan physics. Although it soon became cloaked in political and racial rhetoric, it was at its root a rebellion of empirics against theory, a rebellion of empiricists against the developments in relativity and quantum mechanics, which was incomprehensible to them and hence deeply threatening. See Berchin, 1977. However, the only abnormal thing about this particular eruption was its visibility. No science is immune to it. Tom's book ran ahead into these walls he did not realize were there, because he came from another tradition. But he quickly discovered that the world of mathematics erects walls of its own. That is, in a large part based on a fear that that concern with worldly phenomena, with applications, inherently pulls an informal element into the mathematical world, an element which debases the concepts of rigor that lie at the very heart of mathematics. Indeed, just as much as empiricists fear the theory as a, quote, vector, pulling alien formal elements into their experimental paradise, many pure mathematicians fear the same theory as a bearer of alien informal elements into their mathematical one. On the one hand, there is at root only one reason to do either science or mathematics, and that is to understand what is going on. But understanding is an inherently subjective matter. It is what theory is about, and it is what theory is for. It is also what makes theory necessary. The only important thing, as is true for empirics, is that it be done well. To repudiate it in advance on grounds that it is only theory constitutes a deep but widespread intellectual blemish. Very well.
I think that one thing that is relevant here is that, which is not included in this text, right? Is that, and he mentioned the previous chapter in the book, like he spends a long time in this book criticizing what he calls the metaphor of the mechanism as a general sort of approach to science as such, right? In the book Life Itself, he spends a couple of chapters trying to show that, I mean, there are good reasons why the study of certain physical systems are done in terms of states, and he says that this is a specific thing concerned a specific type of dynamic that allows you to construct a specific type of model. So he shows that states have to relate particulars in the general in a mechanical way. And he says, well, this sort of recursive approach is common to classical mechanics, relativity, and quantum mechanics. That's not really questioning in any of those fields, but it would have to be questioned if you want to make a new theory of biology, because in biology, that assumption is not necessarily a good one to start from. And so
why? Why is it not a good assumption?
Because he says it ultimately leads to a reductionism concerning organisms. Because so like the second half of the book, the second third of the book is about substituting the notion of states and particles and parts for the notion of components in a functional sense. And I mean, it's also clear in the beginning of the text I sent you guys on institutions and so on, that he's constantly making that distinction between looking at systems as structures made of parts, which are states or degrees of freedom, and looking at systems from the functional side. And that the way you would decompose a system functionally doesn't necessarily overlap with the way you would decompose it structurally, right? So the second part of Life Itself is about what is it possible to have a biology that doesn't start from the idea that you're analyzing systems, biological or living systems, in terms of states, but in other terms, which he's calls it a component analysis. And that's why he brings category theory into the picture, because for him, like the truly rational approach to functionality and like multiple ways of entailing parts on each other, and it's a categorical approach, right? So ultimately what he claims actually at the end of the introduction of Life Itself is that when seen from that perspective, physics is a sub-region of biology and not the other way around. Because the class of models that you have in these multiply entailed component systems is actually larger, and the mechanistic systems are actually a region of that. So that's why the generic also comes into the picture, like because he says something which I find very profound. He says, biology is to physics what Gödel was to Hilbert. Like that the impasses of biology with having to think organization placed a problem for physics, for reductive physics that wants to reduce every true statement about a living organism to statements about parts of the system. He says, well, that's homological with saying that all truths about a system can be proved by the particular statements you can make inside of it. Which I think is such a weird kind of approach, but it's very, very kind of telling of how he approaches things. But just to say like that this kind of crusade against the mechanism metaphor as the basis of science is kind of behind this text and the whole book, that just to make that clear. I can read the next. Sorry, yeah.
Yeah, I had the impression like his interest on René Thom from because he proposed like he's developed a catastrophe theory, right? Which is the way you study how certain phenomena you have some like underlying parameters that are in some sense kind of like latent in the system, in which if you are close to that point, by the fact that there are sort of like, we call it like degenerate points in which there are like many variables, like sort of like degrees of freedom that are kind of invisible. So like in a system in which you have like a magnetic system in which you vary the temperature and suddenly you have like alignment of, you observe these phase transitions. Catastrophe theory is all about how these underlying parameters are able to impact more visible and more visible like variables of the system, right? And the Rosen talks a lot about that, about how you have like the functional states that realize a certain function in a biological system, but in its structure it has like underlying degrees of freedom that can kind of impact and have consequences to the function. So like he says how like structure can have multiple functions, and normally a certain function can also be affected by non-functional states. So you have this sort of like richness of that is brought about by the kind of like substrate of the system, and just looking at the functional description, you're not able to get the full potential of the system, I think.
Yeah, that seems to evoke a lot of the open systems philosophy, where a system you can't really say what the function of a system is independent of the environment that it's put into, or it's the interaction it has with other systems. So it's like whatever function a system has, you cannot fully exhaust that system unless you were able to, treat it in all possible environments, which is impossible, right? So it's almost like there's this irreducible openness to, like, if you were trying to enumerate all possible states of some system, you would always miss out something, because it's not a context independent.
Yeah, I mean, it's something to be, we kind of assess this better also once we move forward with the text, but I think it's quite curious that Rosen is praising Henneton so much, because if in his actual work, it's weird how indifferent he is to the state of complex system studies, complex systems theory. Like his notion of complexity is not kind of canonical. His take on emergent phenomena is also very specific. So it's interesting. I mean, I wonder how really in the same direction they are going, because in some level he takes a very different approach, you know. But I think it might become clearer as we go further into the text. I can read the next section. So he says, on information. I use the word information here in a semantic sense, a sense pertaining to meaning, rather than in a Shannonian, purely syntactic sense. Roughly in this usage, information consists of a possible answer to an interrogative question. It is interesting to note that interrogatives themselves belong only to natural languages. The interrogation symbol has no other meaning or logical status. This is actually quite interesting because today that's not really true, right? One of the topics that we've looked at with Pedro and Caron, talking about linear logic, and Girard, it's all about introducing interrogatives into logic, right? So I think that some stuff might have moved past this stage today, but anyway, in a natural language, the answer to an interrogative is generally an adjective of something. It thus comes to modify a noun. This noun is what the semantic information is about, what the information refers to. Indeed, the idea of such semantic information without a referent is vacuous. I do not specify here. I do not specify where such information comes from, but intuitively, we can see that it arises through some process of observation or through some process of entailment that involves other information. In what follows, I shall consider the adjective generic both as constituting information about something and as a source of information about other things. That is, I shall be concerned with what kinds of questions and about what reference can be answered by the term generic, and moreover, with what other kinds of questions can be answered by means of entailments from this term, that is, with what generic can itself imply. The employment of the term genericity as an inferential principle has always played a prominent part in Tom's thinking, first in mathematics and then elsewhere. Just a bracket, I think Tom, as the story goes, that he decided to move to study biology because of Grothendieck. Like when he was a mathematician involved with algebraic topology and all this stuff, and then he saw like stuff that Grothendieck was working on, and he said like, fuck this shit up. I'm not gonna make such big contributions. I better just, you know, do other things and move to smaller regions. Like
Understandable. Understandable why there's not very many other French mathematicians of that age that are famous, I feel.
Yeah. So yeah,
kind of overshadowed the rest.
Yeah, so I think that's I don't remember where I read that, but I think it's actually in the preface, his own preface to Structural Stability. So genericity is prominent in Tom's thinking. It also, although in a much different form, underlies the arguments used by Paul Cohen in his treatment of the independence of the continuum hypothesis and the axiom of choice. In science, things like statistical mechanics could not exist without it. Moreover, the entire concept of surrogacy, the replacement of one thing by a different one, without which experimental science would be unthinkable, is closely related to it. Yet, as far as I know, the links between genericity, semantic information had never been studied systematically. Genericity in these senses makes the vision of Planck, mandating an inherent absolute separation of a presumably objective world from the interposition of the structuring mind, quite meaningless. Stated another way, there is an ineluctable semantic component to objectivity. Very big claims for a very short section. Yeah, I'm not sure I understand what he means here about. I mean, I get what he means by semantic information, but then is this a definition? Is this a definition of genericity, or is just a definition of how he's gonna talk about it? When he says it constitutes information about something and source of information about other things. This is not the definition of generic, right? Or is it? I shall consider the adjective generic. Right, it seems like it's a.
He doesn't define generic here, but he does give us one kind of informal definition in the intro, which is basically as generic as a property which is true, like sort of in a neighborhood. It's a weird way to that he, I think, like informally phrases it.
In the introduction to the section, right?
Yeah.
A property is generic if most of the neighboring things possess it.
Yeah, exactly. If most of the neighboring things possess it. Was that his like?
And or something which is unchanged by arbitrarily small perturbations.
That reminds me kind of if you're familiar, Gabriel, or anyone else with the physics, with how Noether's theorem works, where you do a similar thing. You do these like arbitrary small perturbations, and you show that like the solution is basically stable within that. And that's how being proved. So I wonder if it's related, but I don't know.
But he also defines it in a more, sounds like more broader way, like it's just a proposition that is valid over the full set, right?
Yeah.
Well, the point is it's not just valid over the whole set. It's slightly weaker than that, but like valid almost everywhere in a weird, precise mathematical way.
Like you can define the margin of error between the total set, the general set, and the subset of almost everything that it is valid for, right?
Mm-hmm.
And the measure of this remaining part is almost nothing in some sense.
Yeah.
Yeah.
The way that I remember that he describes it here also is, I just wrote down some notes, is as something called an unfolding, which I don't know what the actual technical definition is, but his informal definition he gives in the intro was a coordinate system for a part of a given neighborhood, right? So you have some neighborhood that you want to say, like if you have a generic property over it, and the way that this generic property is, I guess, like not written down, but the way it's specified is with this thing called the unfolding, which is, he said, like a coordinate system for a part of some neighborhood. So just imagine a neighborhood of something. For example, like I could think of, just because this is the example from the book, like life, right? If you want to, for example, specify what is life, like what are things that are alive, right? In order to do that, you need a definition, right? That basically is complex enough, that it's this coordinate system that's complex enough to span the neighborhood of life in an almost good enough way. So we have certain definitions that scientists and whatever biologists have like semi-agreed on, whatever, a list of a few things, maybe like DNA, whatever, reproduction, blah, 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 blah. And obviously there's maybe some like border places, like maybe like viruses or something like that. But you could say a generic set could be some kind of like, for example, definition of life that spans the set enough such that it can describe it well. That's an example I was thinking when I was reading it, but I don't know if that's actually pertinent.
Yeah, I mean, what I get thus far, like from all the different, just do something here, sorry. What I get thus far from what he's saying is that from the introduction, I think that this connection to neighborhoods right? And the paragraph is actually the couple of statements that he makes there are very right. Genericity arguments shift attention from a specific thing to what a neighborhood of that thing is like. So it's also context dependent and involves inherent impredicativities, which is not clear yet why it involves impredicativities, right? I mean, in being an events theory of genericity, that these two qualities are very clear, right? The three qualities, the neighborhood aspect, the context dependency, or the dealing with the material of the situation, and impredicativity. I think they're clear there, but here I don't understand exactly like how he's thinking this.
Mm-hmm. It seems like it has to do with the movement from what you said, from point to neighborhood.
Yeah.
So it's almost like a move, almost from like sets to topology, kind of.
Yeah.
That's what
it's interesting because it seems like you're dealing with it's like you want to construct an idea of triviality, right? Rather than it being like, it's not the universal from the standpoint of what applies to everything due to logical implication, but almost right. I mean, it's going from down up in such a thing that you get almost to something you can say is trivial, right?
Yeah, because if you think about the idea of properties as grabbing subsets of a set of things, then generic kind of stands as like this weird, it basically stands for like, there's no set of properties that can slice up an entire set.
Mm-hmm.
So I think it's very tied up with the idea of infinity on the one hand, and this impredicativeness on the other. Like with finite, I think with finite sets, I don't think you can talk about generic properties.
Yeah, it's impossible.
Mm-hmm.
Right. So yeah, it definitely has everything to do with non-principal ultrafilters that we've talked about. Has to do with forcing, and
now how about but I think that the least recognizable property he's adding to the list is this idea of surrogacy being very closely connected to it, right? It's not obvious that surrogacy and, a value like the shift from points to neighborhood towards this unfolding, which requires you to have a sort of impredicative, like local impredicative approach to the type of the phenomenon, right? You can't really just discern it and so on. How does that relate to surrogacy, right? It's a bit the capacity to replace one thing for another. It's interesting, like that I think that's like the weird kind of thing he introduced in the middle of all of this, even if the rest is a bit vague.
Yeah, that was a complete jump for me. Like, he didn't explain that at all, and it seems like a really important connection.
Yeah, the way that I understand it thus far is this: like he's saying, he introduced genericity as inferential principle, right? Which he says just at the beginning, right? So, okay, like very briefly, if I understand genericity to have to do with, and he makes the critique in the beginning, right? Like people are associating in science objectivity with reducing statements only to statements about the particular. That would be, let's say, the field of experimental science. Everything which goes from the particular to the universal or to the general is dangerously going into the field of theory in a pejorative sense, because that sort of abstraction or general kind of inference will require something subjective be placed in, right? So with that in mind, and then he's trying to use genericity as a sort of intrinsic semantic component to objectivity, as he says in the end here. the way that I see it related to surrogacy means that, for example, it is possible to understand something about a natural law by studying a couple of cases of it, which is what experiments can be, right? You have a finite set of experiments and you make a judgment about infinite set of phenomena. So, right, surrogacy, replacement of one thing by another, without which experimental science would be unthinkable, seems to be a reference to the fact that you need to move from particular experimental facts to general statements about tendencies, laws, and structure, right? And you do, experiments are surrogates in that sense, right?
This,
Natural.
The concept of surrogate reminds me of this like typical object from Badiou that we talked about, right? The like from what the atom section, right?
Mm-hmm.
That when you have an atom, you can like pick what its like typical element looks like. I feel like it might be related to that. But I don't know.
Yeah, that seems interesting.
It seems like it's doing it in reverse though, right? Because this is going from point to object. I
mean, I think that surrogacy also is connected to points, right? I mean, we broadly been working with the idea that what Badiou calls investigations in being an event, what he calls points or decision points in logics of worlds, is connected with particular experiments, right? Like, does this connect or does it not, right? I mean, his idea of a subjective induction, which I think is connected with generic inferences, implies that from a finite set, right, or potentially infinite set of local investigations, I can say something about a much bigger situation. Mm-hmm. So in that sense, investigations are surrogates, right? You take small interventions to say something about a very big situation.
Mm-hmm. I wonder if points in science could be thought of as, right, because they're decisions of basically yes or no on an infinite set in a certain way that has to conform, right, in a coherent way. But they could be decisions on, for example, like either accepting experiments is valid or invalid, or like the hypotheses that they're testing, right? And the combination of all of them is some sort of point that like coheres together. That could be, for example, right, the set of all whatever these surrogate experiments that allow us to say with maybe some level of confidence that we can feel is okay, to say that some whatever scientific fact has been proven or something. No, that's just completely speculative though.
Yeah, actually, there's something to that, right? With when we say the points form an interior, it's almost like saying, I don't know, I'm trying to like think of it as like you're trying to cover an area and you can't fully cover it maybe, or because of this generic property, or the fact that it's like infinite. So yeah, you need these like surrogate things to get as close to covering it as possible.
Yeah, I think that now that I think of it, like, I think that just one precision we could make in that idea is the following, like, because the theory of points, it's very, well, the whole discussion on the quality of the point, like, the answer, we know it's yes or no. It connects or doesn't connect, but the question to which the answer is yes or no is not really discussed, right? And it's not, the question is not yes or no, and then the answer is yes or no. The question has some quality to it. And I think that the way that you recuperate that discussion in Badiou is because he always claims that, well, a finite set of points or a finite set of investigations does fall under some predicate, right? For example, politically, you have a movement and potentially it interests the whole working class, but for now you've only had a chance to meet up or engage with a certain sector, right? Like the youth or the white youth or something like this. So when you take it like a snapshot, of the series of investigations, it does fall under some predicate, right? But for example, in science, you can say like, these are experiments about this, or they refer to this phenomenon, right? So perhaps you can recuperate a bit the sort of predicative quality of these investigations, the fact that they have a design, right? Like there is some design for the experiment. It's not just we go check yes or no for some hypothesis. So this is very underplayed in Logics of Worlds. And I think in Being an Event, he says a bit more about this, like about there is something slightly arbitrary, but there's some sort of artful approach to investigations. There is a qualitative dimension, right? Of how do you ask a question that can get a yes or no answer, right?
Yeah, I think this question could be also context dependent, but universal on like a certain neighborhood, right?
Mm-hmm.
So it could be for science, the question could be like whether experiments conform with or do not conform with a particular hypothesis, right? So it's context dependent on each individual hypothesis. And the claim could be, for example, that you could, if it's like forms maybe a generic subset, that you could always recover the question from knowing the order of basically the answers of the parts, right? So if you can see yes, 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 no, no, no for the different experiments, you could recover it if it's generic, I think.
Mm-hmm.
I don't know, something like that might do it.
There's a discussion that I think is related on what is on the life itself in the chapter two, that he talks about the sampling, like the limits of sampling. He says that this passage from particular to general, he says, which is the problem of induction. How do you go from the particular to the general? He says, without further structure, the problem of induction cannot be solved in general. That much was originally pointed out by Aristotle, if not his predecessors, and elevated by Hume into a complete rejection of empiricism. And then he discusses that this, like, just by sampling the space, there's no guarantee that you can obtain this principle that goes from particular to the general. And he says that this further structure necessary to deal with inductive problems effectively lies, of course, in the property P, which with which we're dealing. And then he characterizes this property as having this property of contagion, of being able to kind of like take a certain sample X and taking it to like another case. So you have this kind of like sort of like transcendental operator that takes you, that is not given just by like the sample or the thing. And the simplest example he gives is that of like induction in mathematics. You just need this principle of given, like it's valid for one case and you show it's valid for n+1, and then you can go from the particular to the general. So like it seems that you do need this kind of like organizing principle that takes you, like he also comments how like the way that physics was felt, like couldn't feel that there was a revolution to come about, is because before it happens, like the science that will be superseded doesn't have the resources from within it to get out of it, right? So you need this bigger, more general system that embeds it, carries like a new principle to like regionalize the like, for example, he gives the example of like non-classical mechanics and other moments in physics.
Yeah, that seems to be related to this thing Gabriel's saying about the quality of the questions, right? You have the yes, no, which is more having to do with I guess the topology of the space you're trying to investigate. But then the quality of the questions is like these something that is somehow bound together, right? Like they're
Yeah, because a good example of this is that, for example, good experiments for mechanical systems will inquire things that not only tell you about the present state, but facilitate hypotheses or confirm hypotheses about the entailment between states, right? So you, for example, you will try out mathematical formulas that are recursive. So if I give you state one and I give you some sort of elements, I can actually anticipate and predict future states based on this sort of recursive thing, right? But that's because of that particular phenomena you want to study. You making it so that you isolate only this sort of implicative structure is what's at stake. If you, for example, I think that one example that he gives that is really good is if you're a biologist doing experiments, I think he'll say it in this text, like most biologists need to undo the object that they're studying in order to turn it into like experimental information. Like the analytic principle actually needs, because it's so tied up with this sort of state-based approach, will actually structurally decompose the living object into a non-living object, like dissect it. So you don't get to see the functions that are relevant, right? So that would be, let's say, a bad point, right? Your approach to the question, does it connect or not to my hypothesis, already prevents you from getting a positive answer. So I don't know. I think that we can go back to this question afterwards of where does the qualitative part or the, let's say, the formal part of experimentation come in this whole generic discussion. But I think that at least in this idea that experiments they rely on the idea of surrogacy, because you need to be able to sample a finite amount of situations or events and make more general statements than statements about those samples, right? That does treat experiments as surrogates in some sense, right? I can take a part of a large natural system, and that small part preserves properties of the big property that I'm interested in, right? So that's why I think that's the principle behind his critique of experiments in biology. The way we're extracting biological systems from larger biological ones is not preserving the properties we want to generalize afterwards, right? Those are bad surrogates in that sense.
I can read it.
Sure.
Yeah, that's an interesting argument. Go ahead.
On nouns and adjectives. Science, especially physics, claims to concern itself exclusively with objective, context-independent things, completely divorced from the subjectivities arising from a structuring mind. In its simplest form, this asserts that only particular things are real, and that we learn about them through enumeration of their adjectives. Anything else is the province of theory. Parenthetically, however, we may note that it is adjectives that are directly cognized as phenomena, and the nouns they modify are already products of a structuring mind. According to this view, a set of such particulars is not itself a particular, and accordingly is allowed no such objective reality. Therefore, anything based on the formation and properties of such sets is, strictly speaking, outside the province of objective science. In particular, classifications such as the periodic table or linear taxonomy constitute mere subjective intrusions superimposed on the particulars they assort and classify. We learn nothing objective about a chemical element by calling it a halogen, nothing objective about an organism by calling it a vertebrate. Such adjectives pertaining to sets of things, rather than exclusively to the things themselves, convey no objective information about the particulars to which they refer. Indeed, strict empiricists quite rightly feel that admission of such subjective classifications into their science, although of course they do it all the time, is to open a Pandora's box. Once we start forming sets, relations, and classifications on the basis of how particulars look or behave, there is no stopping. We might, for instance, note a basis for relating systems of entirely different character, such as an organism and a dynamical system. For example, establish a relation between a material and a mathematical system, and even ultimately use such a relation to obtain information about the one in terms of the behaviors of the other. From a viewpoint of strict empiricism, such possibilities are simply monstrous. To me, it's not super clear, like who defends this vision of particularism and strict empiricism in biology.
Yeah, it's weird. I mean, I do you remember? I think it's in Life Itself that he gives the example of. He says, biologists today feel that to be rational, they need to avoid finality in teleology to such a point that a rigorous biologist could never say a turtle came out of the water to lay its eggs, because that implies a future state causing a prior state, leaving the water because it's going to do something in the future. Therefore, that's not a rigorous statement. And I'm not sure who said that, but apparently that's the person he hates the most. But he quoted, like when Yasha was reading that the passage on this epistemologist, what's the name of the guy? Bergman.
Bergman.
Yeah. So it seems like there
is this the same Bergman? Bergman? Oh, I'm thinking of something else.
Yeah, I don't know who that is. Bergman talking about Max Planck, and yeah, there are some dialogues here that I think are perhaps like epistemology of science in the 70s was a bit more kind of crude than it is today. Today, people have such weird, sophisticated positions. I'm not sure his critiques are so relevant or so obvious, at least.
Yeah, let us look at these matters a bit more closely. An empiricist concerned with particulars such as water, oil, and air, which he will for convenience collect together as fluids, has no trouble with phrases such as turbulent water, turbulent oil, and turbulent air. Here, the adjective turbulent correctly modifies a particular noun to which our empiricists will grant an objective status or reality. But suppose we turn these phrases around to yield water turbulence, oil turbulence, and air turbulence. We're now treating the turbulence as if it were an objective thing, and the water, oil, and air as instantiations or adjectives of it. To treat this turbulence as if it were a thing in itself, to be studied apart from any specific instantiation, and indeed capable of telling us new things about these particulars, is intolerable to the empiricist. Such an interchange between nouns and adjective provided, for instance, the basis of Schrödinger's question, what is life? See chapter 1. An orthodox empirical biologist finds such a question meaningless. Life and living are harmless adjectives applied to certain kinds of material systems, conveying information about them. But Schrödinger's question turns everything upside down. It turns life into a thing, and any particular organism into an instantiation or specimen or adjective of life. We could have asked a Schrödinger-like question, what is turbulence? Or what is rigidity? Or more generally, what is X for an arbitrary adjective X? Strict empiricists see such considerations as nonsensical at best, hopelessly metaphysical at worst. To grant independent existence to an adjective, to treat it as a noun, involve a mode of analysis they cannot admit. They are willing to partition a noun into other nouns, a process akin to resolving a mixture into pure substances. But the relation between a noun and an adjective is more subtle than that. In particular, it cannot be regarded as a mixture in this sense. There is no empirical physical process capable of making such a separation, and therefore it falls outside experimental analytic modes by its very nature. Nor, for that matter, is there a synthetic inverse procedure for producing a noun that realizes a given adjective, for example, living, by simple juxtapositions or the creation of mixtures. Indeed, there is something inherently non-generic about what can be done by pursuing such simple-minded, syntax-based strategies, on the grounds that only this must be accorded objective status. It is the possibility of such interchanges between particular nouns and their adjectives that provides the basis for concepts of surrogacy. See chapter 6.
So it seems like to me, adding surrogacy allows you to sort of make scientific facts out of like higher order phenomena, right?
Yeah. Yeah, I mean, if you go
Which I
back,
think
like
is very, very, very relevant for the category theory stuff, right?
yeah, I think it's relevant for that category theory things and like to the historical context of the debate, right? The thing we were talking about, like the idea that you're starting to get like books treating complexity as a separate, self-contained topic that is not reducible to the material realization of the complex system. It's a thing in itself, right? The organization is a thing. You can see that instantiated in many fields. I feel like he's kind of opening space for this. It's interesting how he approaches this, because usually people, the way I see people arguing for, let's say, the consistency of studying organization, studying complexity on its own terms, it's more like the way people argue about energy, being partially independent from material. Like, it's a differential. It's only about the differential. It's not really about the material thing that is differentiated or something like this. And complexity and organization seem to be something like that. Like you can shift the material behind it and it remains the same thing. Therefore, it's partially independent or self-sustaining, or you can consider it as something. And his approach here actually reminds me of what we did in the primer, because he's saying that you want a system where predicates and things are interchangeable, right?
Mm-hmm.
Like something can be a predicate of something else, but then you can treat that predicate structure as a thing on its own, and you want to have that flexibility, right? And the whole thing we try to argue in the text that money starts as a predicate for other commodities, right? Let's say the cigaretteness of cows, right? Things like this, and then you can turn it around and you get it into the noun, something that was previously the adjective, right? The predicate for things. It has a similar feel, I think.
That makes it somehow that makes it clear for me. All you had to say was the cigaretteness of cows. This whole page made sense.
Suddenly everything. Yeah, I mean, he goes back to this, but right when he says a statement like a property of a set of particulars cannot be treated as a particular, it's a very nice kind of course, it's hard to find the exact position that asserts irreducibly that you cannot treat sets of particulars as a particular in itself, because I think things tend to be more sophisticated. But I think he's being a bit crude and simplifying here, because I think he's pointing out to the fact that you want a formal approach where that distinction is not made beforehand, right? If a predicate is the particular thing, or if it is the general case of particulars, you don't want to have to choose, like make an ontological choice of what counts as a particular beforehand. So turbulence is a property that many, like an oil, system with oil, system with water, system with whatever fluid can present. So it's a property of the set of particulars. But you want to be able to talk about turbulence as being the particular, right? And turbulence, like water turbulence and other types of fluid dynamics. And now you're comparing the predicates as if they are the particulars under scrutiny, right? So you need to be able to shift that perspective depending on the thing being analyzed, and not because ontologically only thing exists is the things that empirically appear as the particular cases, right?
Yeah, definitely. There's also the topic of models and moving from like just a simple modeling relationship to like this more relational, what like modeling becomes a relation.
Yeah.
Right. So like air turbulence models turbulence, but so does water turbulence.
Yeah. I think that this is really central in life itself. You get the feeling that I mean, it's weird. I mean, I feel like Rosen is the only other guy who has a similar use of mathematics to Badiou, this sort of idea that, like, he's in life itself, he starts with that that little structure, right? For he said, like, I have a system here, a system here. There is some entailment here and some entailment here, and you want to be able to code this into this and then decode the structure, right? So let's say this is a map F, this is some function G, and there is a coding of propositions to the propositions in the second system, and a decoding of the GP inside here to what would be an FQ here, right? And you have Q and you have P, something like this. And then the genius of this is that he says, like, I didn't tell you if these systems are natural systems or formal systems. So you can ask the question of what happens when this is a natural system and this is a natural system. Or when this is a natural system and this is a formal system, or when this is both of them are formal, right? And he says, well, when both are formal systems, these are logical entailment structures, and I can look into the connection of all the arrows. Like, I can actually have a look into all of this, right? When one of them is natural, the other is formal. This is an entailment structure, which is black box, and this or a causal law, right? And this is a formal principle. So by looking at the case of where mathematics interacts with itself, you get to look at the space of possible ways that two systems can interact. And then you can restrict this to fall under this or this. In a certain sense, you could even say, like, this is kind of a big system to a surrogate small system. This is like experimental design, right? And this is the capacity to, like, let's say, guarantee that what happened inside this small system is what is also happening in nature. It's not an inference in the sense of, I know now what's happening in nature. There's no theoretical development. You just made a good experiment, because things that happen in a big natural system are preserved in the small system, right? This would be a mathematical relation between regions of mathematics, like model theory mathematics, for example. And I think it looks like a categorical commutative diagram, actually, right? And this is when you try to model nature and encode propositions about natural laws and work on them formally and predict. So his stupid version of models actually encompasses all of this as cases of it. So you have one language to talk about mathematical structures as opening black boxes of what goes on, a theory of models, and a theory of experiments, and a theory of building theories, right? All in one. So
what is the natural, interpreting natural? Like what?
Yeah,
what
my idea, he talks about this in another book more, one about measurement and experimentation. But I think that retroactively, because he didn't have this idea back then, but retroactively you could say, like, this could be a big natural system, and this is a small one, right? So in some sense, you could say that this is the case. Right, so an experiment is a small system that you extract from this one. But what you want to do is make sure that whatever goes on here is untainted for some properties, right? Like, you don't want to come up with your experiment in a way that it's so distortive of properties of the natural world that you cannot experiment on it properly, right? So it preserves some stuff. So you could say that this is, let's say, this is like a nature or whatever you want to call it, and this is an experiment.
Yeah, that makes sense. Yeah, so you like took a fragment, you created a closed situation in nature that in order to isolate certain variables. Yeah,
exactly. So, I mean, it goes close to that other text we read on experimentation and category theory, when he says, like, you should consider the telescope as a local natural system and not, like, abstract away from its material properties. Like, the set of transformations that a telescope can do materially is a constitutive part of what is allowing you to make the statements you're going to make theoretically later on, right? So there is, I mean, in some sense, and I think that you can find other good texts on this. There is a guy called, I think he's Finnish. I don't know his first name, Uzali, something like this, Uzali Maki. This Maki guy has a really good text called Experiments Are Models and Models Are Experiments. Which he also claims that even in economic theory, in some level, you should be aware that formally there is an interchangeability between them. Smaller model and making an experiment and so on. I think that this is kind of present in the way Rosen is arguing. Anyway, should we continue?
I can read the next.
Yeah, sure.
Yeah, sure.
Yeah, let me just pull it up. Okay, yeah. The concept of genericity arises ultimately in attempts to validate induction as an inferential procedure. Induction is the procedure of arguing from particularities or instances or examples to the general. In its simplest form, it says that if we know P of x1, P of x2 to P of xn, where P is some property or predicate, that is an adjective, and the xi's are samples, nouns drawn from some larger set X, then we can conclude something like for all X, P of X, X belonging to this bigger X, right? If such an inductive inference is valid, then the predicate P is called generic. Okay. Conversely, if a predicate P is generic, then so are such inductive inferences regarding it. Okay, I think that makes it clear. Like for all, it's basically the for all, but done through induction, right?
Yeah.
You don't need to actually verify every single X in big X, but if you are justified in to use induction, then P is generic. Right. We see immediately the close relation between the idea of surrogacy and the genericity of a predicate or adjective that allows surrogates to be interchanged without affecting these relations. These considerations are generally qualified somewhat to allow rare exceptions to expression 9.1. In some sense, the universal quantifier for all is weakened from all to almost all, say by considering our original set X to be a subset of a larger set Y, such that the difference y minus x is nearly empty according to some measure. Genericity in this sense is a property of properties, an adjective of adjectives. Moreover, it is highly context dependent. It depends very heavily on boundary conditions. Specifically, whether an adjective or predicate P is generic or not depends very sensitively on the set X of underlying nouns that are allowed and on how its size is measured. These will, of course, vary from situation to situation. Correspondingly, an adjective or predicate P will be called non-generic if its negation is generic. Of course, in most contexts, a predicate P will be neither generic nor non-generic. That is, genericity is not a generic property of predicates. Wow.
That's confusing.
Yeah, he's really feeling himself here. Genericity and non-genericity turn out to be closely related, and the following examples demonstrate the implications of this. First, it is non-generic for an arbitrary mathematical system to be formalizable. This assertion is basically a corollary of the Gödel incompleteness theorem, and it expresses the generic presence of semantic aspects in systems of entailment, both inferential and causal. Hence, equivalently, the inadequacy of syntax alone as a basis for either mathematics or science, especially biology. Second, given a suitable family of, phi of x parameterized mappings, if A naught is a bifurcation point and delta denotes a perturbation of A naught necessarily arising outside the system, then it is non-generic for delta of A naught and A naught to parameterize similar mappings. Note that this is a genericity condition on the perturbation delta. This is what Yasha you were talking about, right?
Yeah, I'm trying to figure this out myself.
Yeah, it seems complicated, but
So-
I'll just finish this paragraph.
Yeah, go ahead.
Yeah, well, we're going to interpret these results in the context of obtaining information in the sense of answering questions about something by using information about other nearby systems and invoking a concept of surrogacy to justify it. This is a manifestation of what used to be called robustness, what we nowadays call structural stability. When we can do it, it is a manifestation of the genericity of something. When we cannot do it, that very fact reflects the genericity of something else. Both possibilities, as it turns out, are essential sources of information.
So I don't really understand what I don't know if any of you have any insight on the importance of non-genericity. So it says when its negation is generic.
Yeah, so to say that something is not generic.
Oh, it might be something almost like something sort of like an error margin of rather than the generic is right, it's meant to be this like filling, it like fills the whole space, but not everywhere, but like almost everywhere. So if it's the negation of it, it'll be these like very, like, you know how this is a visual metaphor, so I don't know if this is going to help very much, but in the real numbers, right, you can split them up by the rationals and the irrationals. The rational numbers are countable, meaning that they can be basically put out into they can be lined up into a line like first, second, third, fourth, fifth, ordered to infinity. The irrationals cannot be, meaning that they're like a substantially larger size than infinity. That's the whole continuum hypothesis. But what he was talking about with this, when he says about the generic sets, where their original set X to be a subset of the larger set Y, such that the difference Y minus X is nearly empty according to to some measure. It just reminded me of taking like the real numbers and subtracting out the irrational numbers, right? There's so many of them that if you like take the real numbers and then you throw a dart at it, your probability of hitting an irrational number, if you can hit a specific point, is 100%, which is very like unintuitive. Because the irrational numbers are so big in their like quote unquote thickness compared to the real numbers, or the rational numbers, even though they're both like dense in the line, right? They're both everywhere in every single neighborhood. In any tiny neighborhood, no matter how small, you'll find irrational numbers and rational numbers both. But one is like almost the entire thing, and the other is like sort of infinitely small within real numbers, which is yeah. So I don't know. It's just some like rambling thoughts that might help to think about.
Yeah, in life itself, he gives as an example like how 19th century physics got like superseded by today's physics and became like limiting cases, and he calls it situations that are atypical and non-generic in the context of the physics of today. So that's another example of it.
Yeah.
So yeah, non-generic is just anything, any properties that when viewed in some larger set is like a vanishing case.
Yeah, so does it make sense to say, okay, so it makes sense to say, right, that the negation of the abnormal cases gives you the generic case, the generic property of cases, right?
Yeah, I think the non-generic is almost like the differences that don't make a difference. Maybe not exactly, but something like it. You know how we always talk about the differences that make a difference in each context, like scale relativity. This is almost, it feels like the opposite. It's like,
interesting. I mean,
yeah.
It's interesting because I mean, I think it's very. Of course, I'm being the paranoid reader here, right? But when he says that, where is it? The last statement here, that robustness is the case where either I have the manifestation of genericity of something or the manifestation of genericity of something else, right? And that both are essential sources of information. This reminds me of the two sets of investigations or points, right? You get the set of points that connect with the event, and you get the points that do not connect. But the points that do not connect are still sources of information, right? They're not the same thing as, you can treat a point negatively, but that's not the same as not treating a point, right? It's just that the case of the set of things that are negatively connected to the event, all the predicates there are the already known predicates, right? Whereas the set of things that did connect to the event are impredicative. But both are sources of information about what's going on. I wonder if you can connect those two ideas.
Yeah, like from the standpoint of the world, the inexistent and all, and everything that follows from the inexistent is kind of, you could say it's generic. No, it's non-generic, right?
Yeah, but it cannot be the case because the whole point is that it is generic, right?
Right, yeah. Because it's ubiquitous.
Yeah, exactly. The idea is that it becomes, I think this is the thing that really excited Badiou about Cohen and the whole thing. The idea that you can arrive at something which has a negative property with regards to predication, knowledge, and so on, right? It's not, not an already established predicate, by way of accumulating, by way of the common, right? So rather than, for example, classic Marxist approach, which is like Hegelian in nature, which says you will find the common once you find the negative, right? So the proletarian is the negative. Its negativity is fundamental. Because it's negative, it can be universal because it has no discerning properties. It's excluded from property, right? But you get the inverse. Because something is common, then it can be negative in that more profound sense, right? First, something is too common to be predicated, then it defies predication, right? So you construct negativity, you don't rely ontologically on it. Of course, there is a weird dialectic there because you could say the inexistent is negative in some sense, but it's a different type of negative, like it's just not counting, right? It's not counting as a no or as a negation. So I think that this is essentially what interests you about genericity. You can arrive at something which is negative in the classic political sense people give to this power of negativity, but you don't need to assume any ontological detour or structural ahistorical statement about the nature of being a worker, the nature of, you know, sexuality or whatever that philosophers do to find something that is negative that you can use in your favor politically. It's totally contingent, right? You start with something which is just an opening. You start constructing something positively, like a series of investigations, and the result is something that, from the standpoint of the previous situation, is negative. From the standpoint of the new situation, is universal. So you recuperate all the properties of the concrete universal, the Hegelian concrete universal, without having to assume any of the ontological stuff. Nature, by definition, moves towards this. Like, you don't need that, right?
Yeah, that's cool.
So what I'm trying to
I
understand
think
is,
that's what Badiou is interested in too, yeah.
so like what I'm trying to understand is, are these statements he's making about genericity and non-genericity, these ways of slicing a situation in terms of, okay, this is a generic property, this is not, right? And the way that these things divide the space. Does this map onto that description, you know? Because at first it looks as the inverse, right? As if, as Dennis was saying, like this subjective procedure of gathering investigations, it would be singular and it would be abnormal. It wouldn't be common, right? Which is what genericity in Rosen's text seems to be pointing at. Like,
yeah, isn't that the difference between the structural and functional aspects of genericity though, right? Like structurally, it's this like almost everywhere set that's maybe like trying to parameterize some sort of weird infinite subset that you or neighborhood that you're given in some way. And on the other hand, it's also functional in the sense that like it's something that how it comes about is through, for example, in science, maybe experimentation, right? Repeated experimentations and experiments agreeing with one another, and sort of that like building process accumulates to the generic. I don't know.
yeah, I think that the way I would relate this is
because they're definitely related. It's not completely different.
yeah, I agree, but I think I would put it in a different way, which is perhaps it concerns which system you're looking to. Like from the standpoint of, for example, from the standpoint of capitalist world, political procedure is abnormal in the sense that it looks erratic, arbitrary, not properly motivated, or something like this. From the standpoint of the, let's say, the transcendental structure at stake in the process itself, it actually looks more general than the situation itself, right? Like divisions between people that count absolutely in a social world are not that relevant, for example, in a political process where very diverse people can take on very different positions and things like this, right? The case where people are hierarchically tied to certain functions becomes the special case for certain situations, and the general case that many people can do many things, right? So I would say that is it abnormal or is it the most common is actually the shift of perspective that is defining. Intrinsically, it looks to me that it is exceptional and common at the same time, right? It's exceptional because it's an exception to a certain class of predicates that don't really capture what's going on, and common because it's only exceptional because it's such a common subset, right? So I think intrinsically it's exception and common, or singular and common. For example, it's very singular, the type of experiments you're doing. Like it's singular in the sense that it's impossible to understand the intelligibility of why designs were chosen in this way for the experiments if you don't consider specific hypotheses, right? You cannot have, let's say, a regular way of doing experiments. In general, you need to see what you want to ask, right? What are the questions at stake? So it will be singular in that situation, like it's a very singular thread of experimentation. But what it is doing is actually trying to probe into something which should be as common as possible in terms of property, and in a way exceptional because it's not already contained by previously known knowledge. Something like that, I don't know.
It feels that the other text complements all like what we're reading, because it talks a lot about this kind of like overflow of structure of the composition on function, right? So you have non-functional being like driven by this kind of like structural overflow
Yeah.
of systems.
And one more thing on that
Yeah.
point is this shift between a system and its environment. When we previously talked about like
Yeah.
at what point does a body become not an agent but a environment for other bodies? Seems something to do there, right? Like the moment when you're doing some experiment, let's say you have an organization, it stands for some experiment, but because that experiment yields something that allows you to apply the induction to what you've discovered, you've somehow like created the conditions for being the environment for everything else. I'm not really sure how to go further than that, but
yeah, let's continue reading, see what else appears.
Yeah, I can do the next one if you guys want. It
Sure.
seems very mathy, so I can take a lead. A few consequences of genericity. Genericity provides a context that justifies inductive inferences, a way of arguing that because this specimen X has property P, then all X will have it. Conversely, if P is generic, and if we are interested in a particular specimen X, we can obtain information about X by interrogating a different specimen Y, a surrogate. In a sense, the more generic a property P in a particular context, the more such surrogates there will be. The more nouns X will satisfy P of X. Genericity of a property P can be expressed by saying that P of X implies P of delta X, where delta is a small but otherwise arbitrary operation or perturbation of the particular specimen X in question. That is, delta X is always, or at least almost always, a surrogate for X. On the other hand, we have already noted that genericity of a property P is very sensitive to the context. This shows up in a number of subtle ways, both in mathematics and in science. For instance, it is a tenet of reductionism that there are generic ways of analyzing any material system, and that Newton has already basically discovered them. It is also a tenet of molecular biology that it is non-generic for a material system to be, quote, alive, i.e. to be an organism. It's non-generic for it to be alive. Sorry, that comment. Okay. From these presumptions, it is concluded that one, biology is only a trivial special case of physics, and two, we can learn nothing about physics by studying biology. In fact, all of these presumptions are generically mistaken. The conclusions drawn from them spectacularly wrong. These mistakes, woven into the very fabric of contemporary biology, were pointed out by Tom long ago. Here's one example of how subtle the concept of genericity can be. Consider a system of rate equations of the form dx sub I of dt equals f sub I of x1 to xn, where I is from 1 to n. Okay, so this is just a differential equation. So you have a bunch of derivatives that's equal to some function, and you have to solve for what it is. The rate functions f sub I, or rather their differentials df sub I, so these are all the derivatives and for all the different functions, can be written in an apparently equivalent way as df sub I equals the sum of u sub ij times d sub x of I. So this is basically the sum. You're adding up the derivative in each direction, each individual dimension, right? These x sub i's are the individual like x, y, z, for example, dimensions, or however many dimensions there are. And it's just breaking up into a sum. It's saying it's changing this much in this direction, this much in this direction, this much in that other direction. Where we have written u sub ij, so that's the term in the sum, as partial f sub I of x sub j. So this is just basically the partial derivative in the x directions. How much the function f is changing in the direction x sub j. That's on the bottom. Okay. my anticipatory systems. Okay, so this is just an example of some system. Let's see what he does with it. The functions u sub ij express the activation or inhibition of the growth of xi by xj. And hence the differential df f sub I has a different interpretation from that of f sub I, although they seem mathematically equivalent. To study structural stability properties of such systems, we may proceed by, quote, unfolding the f sub I, perturbing them in a presumably arbitrary way by writing delta f sub I is equal to f sub I plus epsilon sub g. So what we're doing here is for each of the different function parameters, so there's some function in many dimensions, and each of the output functions, you're perturbing it in a different way, where epsilon is a, quote, small parameter and g is arbitrary. This constitutes a generic perturbation of f sub I. On the other hand, every such perturbation preserves the exactness of the presumably equivalent differentials. But of course, exactness is a highly non-generic property of differential forms, certainly not preserved under arbitrary perturbations of forms. So exactness has to do with whether the form, this form delta f sub I, right, which is a differential of something, can itself be, or sorry, if the function f sub I can itself be written as a differential, aka a delta of something. So that's what it means for something to be in exact form. It's a thing for math, but I don't think it's too important to go into here. Hence, what looks like an unfolding of f does not yield an unfolding of delta f. Stated another way, there are more ways to perturb delta f, df, than we can find by perturbing f. df has many more, quote, neighbors as a form than f has as a function. So basically what he's saying is that df, which is the differential of f, which seems like it would be something that would have a similar structure to f, actually is much more complicated because you have to look at it in each individual dimension. So it grows in relation to how many, right, dimensions you're going from and how many dimensions you're going to, right? And it grows very quickly. So if, for example, f is from like r n to rm, then df will be basically a matrix of functions of m times n, if that makes sense. It's, you're looking for each function, you look at the derivative in each direction. This kind of situation is itself generic. There are typically many more ways to perturb something than there are things. And then we can think of perturbing the perturbations and so on. So what is meant by an arbitrary perturbation is a highly non-trivial matter. These kinds of ideas provide one entrance into a class of systems I call complex. See life itself for another entrance based on the non-genericity of computability. There you go.
Yeah, in life itself, he associates simulation. The thing we talk about mechanisms being the good metaphor for the scientific approach to life, it has a counterpart in the idea that only a small class of models is simulatable, and living phenomena exceeds that. It cannot really simulate or compute these models, right? So the definition of complexity is connected to that. Like, the system is complex if it has at least one non-simulatable model, something like this.
Mm-hmm. Yeah, this is interesting. It connects how you can. It seems like he's saying that using this like unfolding, you can define the differential here. This delta f sub I equals f sub I plus epsilon sub g. That basically you can define this differential operator of the function itself by just literal perturbations, which is like normally in calculus, it's like considered to be like the approximation. Mm-hmm. But if these perturbations are quote unquote arbitrary and small in ways that you can make mathematically precise, then they can actually define the property of the change of the function. Well, yeah.
this has to do with like defining, for example, infinitesimals in a concrete way in like synthetic geometry and things. What he's talking about, I believe. I don't know if
To
that
make
made any
clear
sense to anyone else. Yeah.
the perturbation, so he's saying that the perturbation, which is the delta Fi, has an exact form.
Oh no, so the perturbation would be the epsilon sub g. So basically he's saying you can get how the thing is changing just by nudging it a little bit and seeing what happens. Right. And you can like estimate this, like basically what you do on a computer when you estimate a derivative, you just like go a very small amount and then you see the difference. Right. Obviously here, this is like some short form for it, but this is basically just saying you move a small amount and you consider that small amount to be, quote, a generic small amount. So if it's small amount, if it's small enough, this is maybe a good way to explain it. If this epsilon sub j is small enough for your specific function, then it can characterize the change of the function at that point. Right? So if you imagine...
Is that connected to Taylor's theorem?
I mean, yes, yeah. In certain ways. But it's... Let me think of how to explain this one.
If it's too weird.
Yeah, let me, 1 second. Can I draw on the screen?
Yeah, let me just make you.
You have to give me a thing.
You have the thing.
Okay, co-host. What do I do again? I go annotate.
Yeah, sorry, I'll just open the space here so you can draw here.
Oh yeah, okay. Options, annotate. Okay, so draw. So for example, let's say I just have some function that looks like this, whatever, okay? And if I take some point here, right? This is x. This point down here. And I want to find the change. Obviously here I see that it's not really changing, right? It's pretty sort of flat. But to find the change, right, what I could do is go a small amount, right? This will be, this distance here will be epsilon. Let me say sub g, this is generic. So this is small enough, we're saying it's generic, it's supposed to be an epsilon, that if you move this amount, right, and then take this point and then take the slope of this line, right, it's pretty close. It's close enough to this point, to the slope of the point, the line at the point itself, right, like infinitesimally, where we can say it's essentially the same. So that's like what the genericity of it means. But then if you take a point here, right, this is like not going to fit that, right? You see here, if I take the slope, it's not at all going to fit with this infinitesimal slope. But it's connecting this like approximation language here of this stepping in epsilon. So this is almost like your experiment, right? In there, talk about the science. It's like a finite thing. And if you want to get closer to the derivative, you can try a smaller one, and a smaller one, and a smaller one. And obviously, this is a very simple function. You can have super complicated functions that look like things like this, whatever. I don't know if that makes sense, but the generic perturbation is basically a perturbation that's small enough in this neighborhood. Remember, he talks about the neighborhoods to classify what's happening in this neighborhood. What's happening in this neighborhood is that the tangent line is pretty flat, right? This is the change. If this is, I don't know, some graph of something, right? Here, if this is maybe a population of something, the population is pretty stable. It just grew, and then now it's stable for a little bit, and then now it's going to shrink after. But by looking at
it's almost like the tangent.
Another, you can.
Yeah, the tangent is like the property, right? If it's
exactly.
Right.
Exactly. It's something. It's like a higher order thing that sits on top of it. That in some sense like doesn't exist in the real world, quote unquote, because we can never like really get to this perfectly. And maybe there's also things with like Planck length and so on that maybe like it's not as continuous as we think, and I don't know, who knows, but
But I was
like, how the world really works is by by doing these experiments, which are like these like small epsilon perturbations. Right?
So from what I understood, these perturbations with the epsilon is kind of like a poor, maybe I didn't understand, but it's like a coarser way to perturb the system, because as he's saying, like if you perturb f by a small amount, there are many directions of x that could kind of like realize that
Yeah.
perturbation, right? So in a sense, you're not. So he also mentions like in the text how, yeah, like the fact that yeah, what looks like an unfolding of f does not yield an unfolding of df. Stated another way, there are more ways to perturb df than we can find by perturbing f. Df has many more
Yes.
neighbors. So,
Yeah, because df grows, because df is measuring, is not just f, like f is from like one dimension to another dimension, but then df becomes this like much larger matrix, which is the multiplication of the two, if that makes sense.
so what I don't understand,
Grows
so
it.
why is it the perturbation on epsilon like generic? Like, is it?
Yeah, so I think the idea of generic is sort of this like, if you can approximate it close enough where we can say it's sort of like, imagine like an infinitesimal, right? You can say it's moving an amount that's so small that the change in the result of, for example, finding the slope of the tangent line by the 2 points is almost the exact same as it would be to the limit. Because the thing is, like, when you actually, I don't know if you guys have done like a like math like analysis course, but when you redefine a limit as in terms of like these like epsilon and delta parameters, which are usually how they frame it, it becomes a lot more concrete in terms of like how things are changing with relation to one another, and that you actually have to like pick something. It's saying for all, you quantify over things in different ways. Like in the standard way, when you talk about a limit, you just say like it approaches it, and like what happens when you go there, like as you approach infinitely. But like rigorously, that doesn't really make sense. So it ends up being like a specific quantification that is essentially this. If you basically just like slap a quantifier before, a couple quantifiers before the statement, it's exactly the formal definition of the limit.
I see.
Yeah, so that's like sort of where the stuff of the approximations, you can make something that looks like the approximations look like the actual thing at the limit. And I think that's kind of the point of the connection with genericity. And this has happened in math too, with things like synthetic geometry.
But just to be clear here, like, because he starts with this example to show that, well, he gives, it's the first time in the text that he gives this definition of genericity in terms of perturbation, right? Property P is generic when you can find this small but otherwise arbitrary operation and it remains generic, right? So Px implies that P of perturbed X is also obtains for it, then P is generic, right?
Yeah.
So he's now associating perturbation, arbitrariness of this perturbation, and genericity. Like you can arrive at you can qualify something as being generic, this property P, if some sort of perturbation is not, let's say, making the perturbed state contradictory with the property.
Yeah, it means that the property P is stable in the neighborhood of X.
Yeah. So
which is like a really powerful statement from the perspective of, for example, science, right?
I see.
Because science, we only like look at finite situations and like individual points, but then we have to infer this like infinite situation and continuous thing from it.
Yeah. Can I draw something? Just, I wonder if this also, based on what you were saying, Yasha, would clarify it, because is it like this, the fact that you can actually have in a region of a curve many different curves that would also qualify? Like if I had a bunch of curves, but at this one point, they all had the same exactness property, meaning like in this region, they all look like the same tangent. They all have the same tangent at this region. Is that why? Is that why the statement that DF has a lot more neighbors as a form than F itself?
Oh, I've actually never thought of it that way, but maybe.
Yeah, I'm just wondering, like,
because everything that you define, right, about DF and is always on neighborhoods of these functions.
Mhm.
So I think there's a good point where when you have this derivative that over arbitrarily large neighborhoods can agree on infinitely many functions, and outside of that, you don't know what's going on. That there's many more intersections of different functions going on in the derivative, yes.
Yeah,
I
because
think
that
so.
actually
And that's why when you have,
fits
for
with the
example, if you're
sheet.
given, so the exactness, what exactness means is that if you're given the derivative, you can extract what the function it's the derivative of from that.
Right.
But you can't always do that, right? So it's like going from DF back to F. Makes sense.
Yeah, I think that the part in the text that goes in the direction of what you're saying then is this, right? It says every such perturbation preserves the exactness of the presumably equivalent, but since exactness is non-generic, it's not like truly the forms can be perturbed in any way, right? So the discourse analysis of neighborhoods can actually be, you can't really trivially claim that not any other curve is not also having those neighborhoods being covering the same tangent at that point.
Yeah. Just wondering, like, if exactness is like a signature, if you can use exactness to characterize a curve, or is it because it's non-generic? Does that mean it can be used to characterize, or is it cannot be used to characterize a curve?
So exactness means, so exactness is something that applies to differential forms, but you can apply it to functions also. A differential form, so that's like this DF thing, which is basically a derivative of a function, but potentially a function of many variables, right? So we say that is exact if it is uniquely the derivative of one function. We can write, if you can write it as DF.
Okay.
That makes sense. If you're given this form, which is some derivative of something, if you can write it as DF for some F, so that means you have gotten the F and it's unique.
Yeah. So in a way, it's similar to that drawing. I
think you're right on that point. It made me think of it in a way I've never thought of it, but yes.
Yeah, it's like a many-to-one problem. It's like a non-injective thing, right?
Ah, that's interesting.
Mm-hmm.
Okay, I think it's my turn, right?
Yeah.
So just so we can finish, I think we're near the end. So he says, so the genericity of catabolic modes. Many authors, for example, Poston and Stewart, have talked about classical catastrophe theory in terms of failure modes of equilibrium mechanical structures. In these interpretations, a catastrophe is regarded as the breaking of some kind of mechanical constraint, such as rigidity. This breaking of constraints is essentially what I mean by a catabolic mode. Correspondingly, an anabolic mode would involve the creation or generation of such constraints. Both physically, since dissipative or irreversible processes are involved, and mathematically, we cannot in general arrive at anabolic modes simply by running catabolic ones backward. In other words, descriptions of modes of system failure do not in themselves yield descriptions of system generation. Such ideas are basic for biology in a number of ways, as Tom has argued. For one thing, the experimental procedures of biochemistry and molecular biology are almost entirely based on the massive breaking of constraints in a system under study. That is, they begin by making the system fail. Then we study the resultant rubble as if it were a surrogate for the original constraint system. Yeah, this is what we were talking about. But of course, pushing a system through a bifurcation in this way means that what we end up with is no longer a surrogate for what we started with. In another direction, all scenarios for the origin of life presume something equivalent to the genericity of anabolic modes. Thus, in effect, analysis, system failure, and system generation are inverse processes. Clearly, all these kinds of genericities cannot be invoked at the same time, at least not within the confines of the original system or class of systems we thought we were dealing with. If we want them all, we have only two choices: to try to find a smaller class, a subclass with all these properties, or else to enlarge our class to a bigger one that possesses it. Speaking generically, only the later option is viable, no pun intended. Why is this a pun? I don't even understand his joke. But okay. It is typically true that the inversion of even synthetic operations such as addition, multiplication, and exponentiation required massive enlargements to permit their inverses to exist generally. And even then, these inversions like subtraction, division, root extraction could not be expressed simply by running the direct operations backward. Although it is easy to get the coefficients of a polynomial from its roots, it's not easy to go the other way.
Mm-hmm.
We already have seen a kind of enlargement that is of the character we need, namely in passing from a rate function such as f, which has only a limited set of neighbors unfolding, to a differential dfi, which has a much larger one. Although we cannot pursue the details here, note that it is necessary to gain information about systems by going to larger systems and not exclusively to smaller ones. Reductionistic modes of system analysis concerned entirely with objectivity, context independent, and syntax cannot abide such information derived from larger context instead of a smaller one. Yeah, for me, the really important statement in this section is this one about, properly extracting the surrogate from the system, from the larger system, right? And how biology is kind of trapped in a problem. I think that this idea here, you can totally apply to the political stuff we're talking about. Like, the idea that this is one approach to organizations as experiments. To say, look, you wanna find smaller units of a social system that preserve properties of the social system, right? Either intrinsically or in their relation to the environment, right? And the idea that you can remove individuals, for example, from that system, and they are the proper unit of analysis is a problem, right? I think it justifies this a bit. I find it really beautiful, this idea. I remember I don't know where I saw this, but a guy talking about some marine biologists for studying dolphins and the kind of collective behavior of dolphins when they swim together and things like this and how they communicate. And the way that they found to study this was to create a mechanical dolphin that swam together with the dolphins. And the question was, what does this mechanical dolphin have to do so that it is seen as part of the group? I think that, it sounds totally crazy for me, but at the same time, it has a feeling that I think it's appropriate, right? How can you make it so that the perturbations that the mechanical dolphin adds to the bunch are arbitrarily small, right? Like they don't matter. Well, if the differences between the mechanical dolphin don't matter to the dolphins, you've captured some information about the dolphins, and not by breaking the dolphin group apart and studying the brain of the dolphin or something like this, but by actually having some intelligence about what sort of interaction, right? How you create a surrogate and how it is actually interacting with the system you're interested in. my head, this has something to do with what we're talking about when we talk about political organization as an experiment as well, right? There's something about the way it is composed that makes it so that it is under the same sort of differences that make a difference than a large social system. Therefore, what happens to that smaller system allows you to make generic statements about the big system itself, right?
I didn't understand in your.
It feels like, I was just gonna say quickly, it feels like a very material way to like put negation into a system,
Yeah.
which I like. Go ahead.
Sorry, Renzo.
No, yeah, I was just trying to understand like the implication you're talking about in political system is that because I was thinking about another example in like how in the brain, like with electrical stimulations, you can like most of the ways you perturb a brain, you can like add noise in like most ways you perturb a brain, you provoke like negative effects, like the person stops doing whatever he was doing, like stops thinking, stops perceiving, stops behaving. But there are only really few ways in which you can perturb a brain and add some meaningful like perception. And I think that's like a really deep thing. But you seem to like be talking about like how in political set, I didn't understand if your point was about like the role of like destruction or about like having organizations that sort of like meaningfully interact with.
Yeah, I think it's more about the
world.
second case. Like,
Second one.
yeah, my point is that what a consequence of not having. I mean, I take this statement here to be, let's say, the version for biology of what we were talking about before when we say it takes some specific composition to actually be able to intervene on a certain structure, right? When he says, if you need to kill the living thing to study it, all the interventions you can make on it won't interact with the property you wanted to study, which is the living quality of it, right? So you need to come up with experiments that preserve certain information or preserve certain structure if you want for it to serve as a surrogate of a larger system. So there is, let's say, a compositional condition on the surrogate preserving the structure you're interested in from the larger system, right? Similarly, even though you can talk about or represent or theorize about complex political structures from the individual standpoint, those properties are no longer sensible to the individual, right? So it's a similar idea of breaking constraints of the system under study. Like the individual is no longer constrained by those structures. So now it becomes, let's say, a abstract representative relation between the individual and the social system. Whereas when you're interested in an organization, it is not representing these constraints. It's actually under those constraints, right? So it is a more adequate surrogate for an experiment kind of quality. So it seems like a similar argument to the one that we've been making about it takes some composition to make some properties intelligible, right? At this sort of more phenomenological level. I think he's making a similar argument when he says, look, you are interested in the living phenomena, but you preserve only the physical structure of the system. Therefore, you're actually uncoupling the two. One is no longer a surrogate for the other, right? Being a surrogate implies that when you take the part for the whole, the part preserved its function in the whole somehow, right? It's still, otherwise you cannot make statements of a bunch of surrogates and learn something about the whole. It simply didn't preserve the properties that would be generic. I think it's in that sense that I see a connection. I'm not sure if it's clear though. But apparently my mechanical dolphin was not the clearest example. Though I really find it kind of an interesting strategy.
Yeah, it's no, I mean, I did get something from it. It just makes some sense. I'm just like confused by what Rosen's saying. Like I get the mechanical dolphin. It makes sense. Like you have this kind of analytic approach, deductive approach, where you try to understand a thing by extracting or projecting its properties down to subsystems,
Parts,
right?
yeah.
Its parts, and then we know, like, okay, the generative effects of parts cannot be like modulo the systems that make up a larger system. You still have some effects that don't necessarily fall from the smaller systems, right?
Yeah.
And those generative effects are somehow captured by this mechanical dolphin thing, right? This surrogate that is somehow inserted into the system without breaking the system's functioning.
Yeah, exactly.
Right. Like, yeah, rather than taking one dolphin out of, or two dolphins out of the group of dolphins and studying how they are.
Or yeah, for example, removing the whole bunch, putting them in an aquarium to see if they start behaving that way again, right?
Yeah, exactly.
And I think in the general case, the without breaking the system's function is like doing a statement is doing a lot of work, right? Like in general, figuring out which differences don't make a difference is like not an easy thing, right?
Yeah.
How much you can perturb the system in order to still preserve certain things and then learn something about it, I think is like a very specific, is almost like the creative part, maybe.
Yeah, you know, like this reminds me, you know, that Jakob Uxküll guy, the guy who wrote the book Foray into the World of Animals. He was a biologist as well in the turn of the 20th century, and he was the guy who invented the concept of environment, pretty much, like Umwelt. He's the guy who turned it into like a strict thing. And his method of study was like selecting an animal, shifting the environment to find out what counts for the environment and what doesn't. Oh my God, I'm afraid of opening this video, you guys.
They're actually being used for animal emancipation. So
Yeah, in this case, it's like the audience that watch, like the system of SeaWorld. I don't know if you have SeaWorld in Brazil, but it's like the system of audiences watching dolphins. If you can replace that dolphin with a mechanical one, then no one notices. Then it's
yeah. I love that there is a Turing test. Isn't there a Turing test kind of quality to all of this?
Yeah,
right?
exactly.
Like I cannot compute, meaning I cannot reduce the problem of Turing computation to some algorithm to define if it's, you know, behaving like a human, but I can make it interact with a human in a way that no perturbation makes it abnormal, right? There is a weird Turing-y feel to this,
that's a good point. Yeah.
right? But I mean, I understand his argument to be this, that he says breaking constraints, he calls it a catabolic thing, and he associates it with an analytic evaluation of structurally decomposing a system into its parts, right? And the anabolic one is the one that allows new constraints to appear. And he's then saying that biologists tend to like make experimental procedures based on breaking constraints of the system under study. So you want to force biological entities into context independence so they can become objects of experimentation. But this context independence already breaks a bunch of constraints, right? The mechanical dolphin example is about inserting something into the context-dependent constraints in such a way that they remain in place. If you're able to do that, you can learn something. Like this is a way of extracting information as well, right? That's why I mentioned Uxküll, because, for example, he would take a bee or like a tick, I think, and then he will show that like you can shift temperatures around the tick, and it doesn't react. you can change the composition of the air and it doesn't react. But if you change, I don't know, the presence or absence of some pheromone or something, then it reacts. And he started understanding what makes a difference for the tick based on perturbations that are irrelevant and perturbations that are relevant, right? So, and he called the system of relevant perturbations the world of that animal, right? It was a really huge influence for Heidegger in his theory of worlds and so on. So it has that idea of sometimes you can investigate the structure by leaving the constraints in place and seeing what can be removed. I mean, it reminds me of like Tononi's as well, like what you can remove and things remain generic, right? You can perturb it in this way, but things still function. Like he kind of points to the idea that organized systems should be experimented with from that perspective, right? And not from the perspective of breaking down parts. It also has a Grothendieck feel with the whole quote. Remember that quote became famous, like that he solves problems by putting problems in like like people try to break a nut and crack it open, but I tend to think of putting the nut in like a watery solution, and it slowly kind of. I mean, he has really good one line.
Pickling.
Yeah.
Pickling.
Yeah, Grothendieck and pickling. I don't think I've seen anyone make the connection, but right. But that leads you to this idea that you need to sometimes go towards a larger system under which you can now think the constraint, like enlarge your class to a bigger one, right? That's the only way to turn systems that you don't want to break their constraints into meaningless parts. The other way to turn it into a particular is actually to embed it into something larger, right? For example, the mechanical dolphin, there is a huge class of behaviors for the mechanical dolphin that exceeds the class of behaviors of dolphins, right? And you're actually putting the dolphin experiment under this larger thing, and that's your kind of space of variation now, right? So the behavior of the dolphins now becomes a special case. Yeah.
Yeah, should we just finish?
Yeah, let's just.
Yeah.
Whose turn is it? Mine or Renzo, right?
Maybe mine. Some conclusions. I have tried to indicate how the concept of genericity is a powerful source of semantic information. First, by discounting the presupposition that a sharp line could be drawn between objective reality and the subjectivities of a structuring mind. Such a line will leave us only with particularities. It would expunge all classifications and eliminate all notions of surrogacy. I concluded that such a presumed partition has itself no objective existence. I then characterize the information in a semantic sense in terms of interrogatives pertaining to external reference. Thus, information becomes associated with propositions P of X, in which the referent X plays a central role. Next, I argued that the roles of P and X could be interchanged, so that P becomes the referent and X becomes a property or adjective of P. Such an interchange is often called abstraction of X. I illustrated such interchanges by means of the familiar adjectives rigid, turbulent, and living. I indicated how these interchanges provide intrinsic classifications and surrogacies into the world of particulars we started with. I then turned on to the concept of the genericity in terms of a context in which it maximizes surrogacy. We saw how it becomes a source of information about a particular Y, entailed from a different particular X, using the genericity of P to entail P of Y from P of X. Most of these considerations are already explicit or tested in Tom's book of 1972. I hope that my limited remarks will draw attention back to the truly radical facets of the book and to some of their fundamental implications.
Yeah, for me, this is the big paragraph, right? I think this is a really cool definition.
Yeah.
That generacy has relation to maximizing surrogacy.
It's all related to this like
substituting this like finite like experimentation or whatever the adjective for other forms that aren't science in to this like I guess get conclusions from it, right? But it also connects to like
And
you
it
want to
reminds-
learn something about a neighborhood, but then you can just perturb it in like finitely many ways. And if you do it in the correct way, then you can maybe, hopefully, get some truth from it. I think that might be the idea, but I don't know.
and
So
it
we just need
reminds
to
a lot
figure
of-
out what is an organizational perturbation.
Yeah,
Well, I think that's the easy part, actually.
and the topology is the whole thing too. Like,
You could, I mean, that's almost a definition of political practice, like a bunch of organizational perturbation.
Yeah, things that don't actually change things that much.
Yeah, I think that's the whole point, right? You want, for example, I think that's the issue, right? For example, what sort of intervention? Because it's nice to read this now in the context of the things you were talking about before, right? Like we've been talking about how does composition of organizations connect with what type of information they can extract, and how is this connected with the ways it can interact with the world? So it seems like interaction is connected with perturbations, right? Information is connected with intelligibility, and this sort of sampling and the way you sample and the way that these samples are organized and so on, that's connected with, right, particulars, abstraction, and the surrogacy part, right? Like surrogacy is connected, for example, with, and it's interesting that it's weird that it gives you an experiment from like the equations of rates of change and so on, to talk about, let's say, connection between experiments in biology. Usually you would go to an example of that to talk about, say, the unfolding of a law, not to also extract interesting ideas about, sampling in terms of experiments and perturbation in terms of the experiments you do. I think it says a lot about his way of using mathematics. Like, it's never the example of, like, he doesn't go there to talk about, is nature totally captured by this mathematical equation? It's always like mathematics is the most crystalline set of ways of talking about the experimentation, mostly, but I mean, for me, like when he talks about genericity, surrogacy, and information, like it does look like he's saying, like it's pointing to the direction of a political procedure is the most generic, meaning you can know the most about the most general properties of a situation that is larger than that process. The more it can, let's say, find meaningful parts, meaningful samples, right, whose interaction with perturbations are preserving property. Right? For example, a political process that can only work with one type of tactic, it's probably highly non-generic, because there's only one way to extract information, right, about the whole.
Yeah, I think it's also important that genericity is always in reference to a specific neighborhood, so it's always context dependent, right?
Yeah.
This notion of surrogacy sounds really similar to the discussion from surrogate reasoning, right? Like the way you go from Py to Px, you're like in the target system in which you're able to do these transformations, right? And then you can come back and say something about X and Y.
I really think so, that there is a connection there. And because he makes the connection between neighborhoods, surrogacy, and experiments, I don't know, it really, I think, suggests a bridge, there. like 2 meetings ago, we were talking about this surrogate reasoning text and saying that it could connect with those texts on experimentation. It looked like we had a connection. I think that for him, the connection is established, right?
It seems direct, yeah.
Yeah. And I think that this is something that that is crucial, perhaps, and not that obvious in the things we've been talking about. Because, for example, we speak of, I don't know, political process involves creating some sort of body of interventions, and different parts are being combined in ways that are singular in the sense that they wouldn't be combined otherwise. And it's easy to get lost in the fact that, I think something we mentioned today, that, well, this is very singular, therefore very abnormal. It's relevant because it is exceptional, right? Something is happening there that is not happening elsewhere. And I think that even the thing we were talking before the meeting about being an event and the way that it connects to logics of worlds, and the way that he argues in this text, it points to the fact that the other side of this coin, right, what makes this singular path interesting is that it allows it to make very broad statements, right, or to see very, very essential characteristics, right? This is something that I think that is a really good qualifier to why we can call political organizations political experiments, even though, of course, you cannot reduce this to a sort of epistemological. I organize myself politically because I want to know the world. The cool thing about this approach is that wanting to know about the world and changing something about it are actually the same process, right? Like you can only make some information relevant that wasn't relevant before in a political world through some sort of sampling of things whose perturbations are surrogates, allow you to treat it as a surrogate for something much larger, right? So it actually captures this sort of double-sidedness of genericity we were talking about, that it's highly singular in the sense that it requires a very, very kind of non-trivial choosing of what samples and what investigations and so on, but it also has a very strong foot on this common dimension, right? Which I think I really think it's one of the really cool consequences of our current project, because it doesn't limit the role of theory. There's a reason to have political theory and things like this, but it does put this sort of access to concrete kind of intelligibility of the social role as a function of organizations, like
And when you say as a function of organizations, you mean given organizations, you can like somehow, I guess, determine whether by experimentation or by experience that, like, in some sense, the topology of these organizations and how the perturbations make or don't make differences, right?
Yeah, exactly. The sense that that organizations are a better surrogate for what actually counts and doesn't count in a world than, let's say, the direct theoretical description, right, of the world.
Yeah. And I guess with the organizations also, the structure is kind of trivial, right? It's kind of given like immediately in a sense, right?
What do you mean?
I mean, like, generally when you have organization, the structural dimensions, like, for example, boss, worker, are usually kind of like inscribed into the organization itself, right?
Yeah, but this is exactly the thing that I think this thesis makes clearer. Like, different compositions of political organizations are like, you know, that's the field where it's the equivalent problem to this issue he was talking about considerations of the anabolic dimension, right? You can organize in such a way that some things are not questioned or not put into question by organization. Therefore, you won't get an answer about how intense that constraint is, how relevant it is. You won't learn anything about it, right? Like to summarize, to simplify it a bit, but to point in a direction that I'm really interested in. We already defined in our approach that objects in a social formation are these complex combinations of different modes of exchange, right? Or different modes of constraint, we could talk, right? Reciprocal constraints, contractual constraints, value constraints, things like this, right?
Yeah.
So what does it mean is that when I create an organization, a political organization that is trivial in the contractual sense, it's a legal NGO, trivial in the communitarian sense, that it just reproduces patriarchy, it's only made of friends, it just goes with the flow, like the least costly path on the mode A and mode B, but it is a cooperative. So it's actually going against the grain on mode C, right? It perturbs something, it creates some abnormality on one mode, but very trivial on the other ones. Well, it's most likely that it will only learn things about the world of value, easier paths, interesting solutions, inventive things, whereas it won't know anything about how objects in that social formation are also constrained by those other two modes, because it just took the least costly path on those dimensions, right? So suddenly you have a theory of a complex social system and surrogates, which are smaller organizations or smaller systems that are, let's say, up to the task of investigating specific aspects of these large objects or large systems, depending on what constraints you get to preserve, not preserve in the sense of reproduce, but preserve in the sense of interact with, right?
They're like a local representative of the parameter space, I guess, in some sense.
Yeah. So in that sense, it's a surrogate, right? You cut it off and then you change something. For example, you negate a community structure. So it's, for example, racial relations, gender relations are different in it. So you're perturbing it in that way. You're pushing it against the grain in that dimension, but it's an NGO with private funding, right? It's perturbing things, it's stretching things in one direction. It's trying something out or negating something and trying a different constraint on one level, but keeping other levels in place. You can kind of derive from there that you won't make certain aspects of the social formation intelligible from that perspective, right? So you can start asking the question of what organizational structures are homogeneous with the most generic properties of the social formation. So for example, the Soviet Union is an object that is as complex as the global economy in a way, right? It involves communitarian state, value things, plus kind of new structures and all those levels. And it can be affected by all those levels as well, right? So you can actually get a different worldview from the standpoint of the fact that you're able to intervene on all those levels at once, right? So you see, like the sort of kind of interactive problem of interaction you can get, and there are problems. Those are problems that will be combining composition in the sense of how they are composed within each logic, but also how they compose each logic to form these objects. Intelligibility, because depending on how you're composed, some things will simply pass you by. They won't make any difference. You're not really, they won't appear as a resisting kind of part of the environment against your action, or they won't really be relevant, right? And those two things are connected with how you interact. Like you're able to change some things, but unable to affect other things. And I think that this let's say, puts organizational design, issues of scale and size on like a very different theoretical footing, you know?
Yeah, and I also think these, for example, these like pictures we often draw when we think of these perturbations are usually not very reflective of what like these real systems are going to be like, because very often, for example, in one dimension, like the scales, like you said, matter a lot. Like in one dimension, a very, very small perturbation can make a huge difference on another scale. It'll like be much more smooth or something, or on another dimension. So, and these can be huge systems with like insane, like think of, for example, this was the example Renzo said before of like doing perturbations, something like the brain, right? Like doing experiments to someone, for example, like let's say perturbations inside an MRI machine, right? Or fMRI machine, so you can see what's happening. So obviously being in the fMRI machine like limits certain things that you can do, but you can do certain things and see what changes. And they've been able to get certain things about the brain from that, but not a whole lot. Well, I mean a lot, but.
Yeah, but for example, I think that this is a really good place where you see how this is relevant for neuroscience. It's something I was talking to Renzo about a while back. For example, people see that there is therapeutic and medical use of LSD in treatment of some things, but you cannot treat it as context independent. You need to introduce the psychotropic and, let's say, social interaction of some sort rather than another. Like, you see, it kind of goes in the same direction. Like, you need to preserve a more complex system of constraints in order for the interesting properties to be perturbable, right? It's not simply a matter of, that's why I'm not saying simply that, like, the interesting distinction we start making is that there are two levels of constraint breaking. You can break constraint because you made yourself heterogeneous to the thing you're interested in, which is Rosen's example of killing a creature to study how it lives. You first lose a property before you interact. So you break the constraint in the sense of exiting the world where that constraint exists in a way, right? Which is different from perturbing the constraint or pushing it in a different direction. But that requires some homogeneity to be preserved, right?
But also it's removing the constraint in order to allow for greater perturbations, right? So you're removing the constraint of the animal's life in this example, which is grim, in order to allow for the perturbations of cutting its brain open or whatever. Right?
Yeah, but this is the point. Like, what starts getting into question is when you kill the animal to study it. Of course, you can have a much vaster kind of set of perturbations you can make, but you actually might lose
limits a lot.
Yeah, it might actually. This is, I think, Rosen's argument. Like, it doesn't necessarily make them more relevant. Like, I now have a larger analytic space, right? Because once you understand that semantics, there is this objective semantic dimension, or this properties can be internal to the object and not external, that we are subjectively abstracting. You can actually abstract too much by being too analytic, right? You might have to stop earlier. I mean, we can translate it into a problem of you need to preserve some resolution or some level of what counts as a part. You might be capable of cutting it further, but you might lose the functional parts in the process, right? So when you look at the tissue, you're looking at it structurally and materially, but you can't really see what the tissue does functionally, right? And it might have many functions, and not functions you can recompose from the broken constraints system up back, right? So that idea that you need to preserve some homogeneity between the surrogate and the thing you want to study divides this theory of constraint breaking into two. You can break too many constraints and lose the information you wanted to learn about, make like the bridge uncrossable, right? or you can remove a surrogate that preserves enough of the constraint so that what happens to it does in fact allow you to make more general statements about what happens elsewhere. That's the part that I think is relevant, you know, like for us.
Yeah. Mhm.
Guys, I'll need to run now. Not only
Alright,
is,
yeah,
is a
I'm getting
storm
tired.
coming, but I need to cook.
Oh, good night.
See you guys.
See ya.
Yes.